Hey guys, welcome back to CS395. This is week 5 and today we'll be talking about fuzzing basics and scripting your exploits. And I have been waiting all 5 weeks to teach you guys about scripting exploits. It's going to be the bread and butter of everything we do from now on. All of our exploits from now on will be scripted in Python using Pwn tools, and I'm super excited because it makes everything a lot easier, a lot less tedious, and makes us look like awesome hackers. So we'll get into that soon, but first we have to talk about fuzzing. And fuzzing is a software testing technique where we basically just throw a bunch of unexpected or random inputs at a program to test if it's vulnerable. And we know it's vulnerable if our inputs cause it to crash or throw an exception or operate in some way it's not supposed to. And we can use this to discover a bunch of different vulnerabilities, but mostly what we're interested in is the buffer overflow, the holy grail of this class. And I'll be teaching you guys how to use a tool, the very basics of how to use a tool called AFL++. That is basically just a super fast fuzzer that generates random payloads and throws them at at binaries a lot faster than any human could. So we'll get to that. Here's a funny joke you can read and laugh at on your own time because we're moving on. So this is the slide from the first lecture, if you remember that, when we first started talking about buffer overflows. And I'll be going through all these bullet points again. And for each of them, I'll show you a new way to go about doing them better. That's like a million times better than the way you've been doing them up until now. Using Pwn tools and Python and scripting, all of this is going to be a lot better. So now we're going to talk about AFL++, and I'll show you the very basics of how to use it. Now, first I should just say that you should never use AFL in this class because the binaries that we're giving you are pretty simple and designed to be pretty easy to spot the vulnerabilities in them. So using AFL kind of defeats the purpose of this class. And it's totally overkill anyway because it'll do this thing goes wicked fast. It's like, industrial strength fuzzing. So this is for like on a big project if you're, in the industry working on like, I don't know, if you're trying to like find a buffer overflow in Microsoft Word or something, that's when you would use like AFL to see if you can catch like an easy buffer overflow without having to stare at the source code for forever. So let's just get into the demo here. What you want, or first I should say that this is the program that we're going to be fuzzing is just the same binary from the first week. It's just the classic gets overflow here that we use to try to call get shell. And there's 2 folders here that you'll see. We have an in folder and an out folder. And the in folder just contains just a random file here that just names it hello. That contains random text that tells AFL that, hey, this is what an input to this program should look like. And since there's only one fgets and it asks for text once, I just have one line here of a bunch of random junk because it doesn't actually matter what you type in. And AFL will mutate that and randomize that until it finds combinations that work and crash the program. And then we also have an output folder right here that will just contain all of the payloads it found that managed to crash the binary. So without further ado, let's get into running the fuzzer. But I should also mention first that we have this -q option here, and what that means is that, sorry, let me just zoom this in so it's easier to see. Yeah, we have this -q option flagged, and what that means, it stands for QEMU, which is an emulator. And AFL is designed to be used best on source code, but it makes mutating a lot faster, and it lets AFL make educated guesses on what its input should be, as opposed to using it on just a raw binary like I'm teaching you guys right now. Makes it a lot slower, but as if you're hacking, you usually don't have access to the source code of the binary you're trying to exploit. So we'll be accounting for that today. So we run it in QEMU mode, which is slower, but it's more realistic. And we're all about realism in this class. So we use -i and -o to specify the input and the output folders. And then we'll just type in /vuln to let it know that's what we want to run. And then we'll let the fuzzing begin. So it looks like everything worked out there. And it doesn't like that my screen is so zoomed in. So we'll just zoom out. And then you can see it has this like really beautiful menu, which is kind of crazy. And there's a lot going on here that we won't worry about. All we care about right here is the total crashes, specifically the unique crashes. So it's already found, in a payload that crashes it. And since there's only one way to really crash this program, that's all it's going to find, I think. So we could leave this running forever. You can see it's already run through, 539 different tries. It's doing a whole bunch of stuff. If you were doing this on, a real big project, you can see it's only running on one core here. You'd want to allocate it more cores, but if you want to do that, you should look at the. If you're interested in any of this and you want to get more in depth, then you should look at the GitHub page that I linked on one of the previous slides. And this is all we'll talk about it today. If it'll let me close this, please. It's stuck open right now. So I'd love to Control-C out of this. But it looks like it's holding my computer kind of hostage right now, which is pretty scary. Hey guys, it's Sam from the future here. In my excitement to get to talking about Pwn tools, I forgot to show you guys what AFL actually did when we were running it. So you'll remember that I was talking about how AFL essentially just brute forces a bunch of payloads to the binary until it sees something that crashes. So once it finds a payload that crashes, it puts it here in the out folder that we made. And then we'll just go into default. You can see that there's a crashes file. That's what we're interested in. You can see there's two files here. There's a readme that we're just going to ignore. And right here, this really weird looking file is actually it's a payload for us to use. So if we take this payload and then cat it and pipe the output of that into our vulnerable binary, we'll get a crash. And that's what AFL does. It produces payloads that crash the program so that we can look more into this and say, like, okay, well, why did this payload crash it? And do some reverse engineering there to figure out how we can turn this into an exploit. Okay, that's it. Enjoy the rest of the lecture. Okay, we're back. I managed to free my VM from the CPU melting clutches of AFL, pushing my CPU to 200% horsepower, which is very impressive. But let's just step away from that for now. And we'll get back to the lecture where we can finally talk about Pwn tools. Yes. All right, Pwn tools is a Python library specifically for developing exploits. We'll be using this for the rest of the semester. You guys are going to get very well acquainted with Pwn tools. It automates a lot of the boring stuff, a lot of the tedious stuff. Makes so many things so easy. And I highly recommend if you're confused about something or want to learn how something works, I'll, of course, be running through some scripts and making one with you guys and explaining everything I'm doing. But if you're interested in learning more, you should please read the documentation. Pwn tools can do so much. We could teach a whole class on Pwn tools and not cover everything it does. But yeah. So now we're on the second step of a buffer overflow, which is determining the distance from our vulnerable buffer to the return address. So back when we were doing this the noob way, we were like, oh, okay, I have a vulnerable buffer here, and there's 2 integers above it, so that's 8 bytes, and then the base point's another 8 bytes. No. We're never doing that again, because now we have access to cyclic, which while Pwn tools is, for scripting in Python, it also has some command line tools. Cyclic is one of them. And basically all it does is that, if we run it here, we say cyclic 200, it generates a 200 character long string, as you can see here, but it's a very special string. And what makes this special is that if you grab any 4 characters from it, any series of 4 characters in the string is completely unique, and we can put it back into cyclic with cyclic-l, and it'll tell us which position in the string it is. And that may sound boring and pointless to you, but think about it like this, all right? You run your binary in GDB, and you want to see, I think my input will crash this program. If I have, if I give it 200 characters, I think it'll crash, but I'm not entirely sure. So you run cyclic 200, you copy your payload here, run it in GDB. When it asks for input, you just paste it and let it go. And then you keep stepping through in GDB until you segfault. And then you look at the top of your stack, which you can see here in the stack pointer. The first 4 characters on the stack, you just copy and paste those into cyclic, and then it tells you it's 22 bytes. So then, using this dark magic that I just taught you, you know that the distance between the return address and your vulnerable buffer is 22 bytes. And you didn't have to do any math, you didn't even have to think about it really, now you just know. And I'll demonstrate this later if it doesn't make any sense right now, but this is very helpful, and and a lot faster than I'm doing math, and you'll make a lot less mistakes. Anyway, now we're getting to the actual scripting goodness, and we'll talk about how much easier it makes creating payloads and changing payloads. Before we were, the first lecture I taught you guys to use Python on the command line to write to a file and put your payload in there, and then we'd cat and redirect our payload into the binary. And then, last lecture I told you guys to do the Python 3-C thing, and that was a whole nightmare of scrolling, and making changes was impossible. But no longer do we suffer, because we can just write our scripts to a file. We just make a shellcode variable and put our shellcode in there. You can just save our addresses very easily. The P64 function is amazing, and I'll talk about that later. And our payloads are as simple as just easy Python scripting. You can just put your variables in, so changing stuff on the fly is now lightning fast. Just open up your script in Vim or your favorite text editor, which should be Vim, and then just do everything a lot quicker, a lot easier. That brings us to our last step, which is Pwn Tools has done a lot for us, but can it does it help us run the program? Does it let us inject our payloads easier? It's already done so much for us, and my answer to that is, of course it does. Pwn Tools does everything for us. We can start a process, send our payload, and then open up a shell, all in just 3 lines, which is amazing. It's unheard of. It's phenomenal. If you guys remember back in the first lecture, I taught you guys that really strange trick using like a cat to keep standard input open so that you could interact with the shell if you got one. Now you can just use this interactive function here. You can spawn a process and assign that to a variable, and I'll talk more about this in a second. And sending your payload is just so easy now. So we'll get into a demonstration. I've been all talk up to this point, but now I'm going to show you guys some muscle, how the big boys do this stuff. So you can all flex on your friends and be the coolest binary exploitation master in your friend group right after you see how to do this stuff. Alright, so here we are back in the VM, and we're going to do, we're in the week 5 folder, but I pulled the buffer overflow from the week 1 challenge and from the week 1 demo, and we're just going to do that again here, but we're going to script it this time. And I'll show you guys like the thought process and how to script your exploits. So I already have one here. This is an example for you guys if you want to look at it later. This is what it will look like, and we'll just be writing this again from memory right now. Not from memory, but from skill. So the whole exploit here, we have a gets, which gives us a guaranteed buffer overflow, and we have a get shell function that we want to call. So as we all know, we would just want to we want to find the address of get shell, replace our return address with that, so we can get our shell. So the first thing we want to do is find our offset, as we've done so many times before, but this time it's going to be so easy. Let's just say cyclic 100 should do it, since these buffers are kind of small. So we'll just copy and paste that. Easy. GDB vuln, and then we don't even need to set breakpoints. We just run it, paste, continue. Oh no, it looks like, oh, it's seg fault. What? Let's take a look at what's wrong here. Looks like GAAA was on the top of the stack, so let's copy that. Quit out of this. Cyclic -L GAA. and we can see that the distance between our vulnerable buffer and our return address is 24 bytes. So what are we going to do with that information? We're just going to create a Python script. We'll just call it demo.py. The first thing we're always going to do from now on is not import, from pwn import all, or input star. And that'll give us access to all the absolutely delicious functions that pwntool provides. And we'll just start by creating a payload variable, and we'll start crafting our payload. So we wanted, I believe it was, I actually don't remember how many bytes it was, 24 bytes of junk before we start actually putting down anything interesting. So 24 A's. All right, now what's the next thing we want? Next, we want the address of get shell, so we can overwrite the return address. So before I showed you guys how to do that in object dump, but there's a cooler way of doing it in my opinion. You can just do info functions in GDB, and that'll show you the addresses of all the functions in in the binary. So we can just easily see that this is our get shell address. So I will try my absolute hardest to copy and paste this, but VirtualBox does not make it easy. Unfortunately, pwntool does not make copy and pasting things any easier. All right, we got it. We can quit out of GDB now, and we'll go back to our demo.py. And then we can just add that. So now you might be thinking, well, Sam, hold on. You just copy and pasted an address straight out of GDB into your payload. Don't you know anything that you have to reverse the order of the bytes in little endian? And normally, under any circumstances, you would be right. But this is pwntool, baby, so we can just P64, which stands for pack64. And that does all that boring stuff for us. This will convert our hexadecimal address into little endian, so we don't even have to worry about it. It's done, easy. No scrolling, no losing track of the address. It's all just there. Sorry, I don't get money for advertising pwntool. I'm just very passionate about it. It's a great product, or not even a product. It's a great project. So yeah, now I believe that is our completed payload. So all that's left to do now is we want to tell pwntool to run our binary. So we can just use /vuln because it knows that it is in the current directory. And that will create a process that'll run it for us. And then after it starts to run, it'll hit the fgets, and the program will hang until it gets an input. So to send our payload, we will say send line, because we're just sending one line here. You can just type in payload, which is excellent. And then if everything worked out well, then we'll have just been given a shell. So to interact with that shell and keep standard in open, we will just do io.interactive. And that should let us type whatever we want in the shell. That will transfer standard in control from the process. The script here has control of standard input until we hit interactive, and that gives standard in control back to us on the command line, so we can type whatever we want. So now I believe if we just do Python 3, not exploit, demo.py, run that, you can see it ran the binary, switched to interactive mode. Now if we type, let's try running some commands here. If I can remember how to type in English. CS395, and we have a shell. Amazing. So hopefully now you can understand what makes pwntool so great, why this is so much easier. And this is what all the pros do. Everyone on CTFs, all the cool guys script their exploits, and everyone shares them. And this is how all of our assignments will be done from now on. unless otherwise stated. So let's get back to the presentation and dissecting what we just did. I basically explained all of this already, but here's just some more notes, as well as links to the documentation for each of these functions that I mentioned. I suppose it's worth mentioning that I name my processes IO just because that makes sense to me. So that spawns a process, but processes in Pwn Tools are wrapped in what's called a tube, and that's something you should look at because tubes are basically just a wrapper that allows us to do all this fancy, changing standard in. It lets us do our interactive stuff. It makes all that possible. So send line, there's a bunch of different variations. There's like send all and just like send a certain amount of bytes, and you can find all of that in, I believe, the tube documentation. So now you might be wondering, well, Sam, what if what if my exploit doesn't work and then I have to like do it in GDB? Do I have to redo everything manually in GDB, or can I just use it with Pwn Tools? And that was a silly question because of course you can do it in Pwn Tools. You could do everything in Pwn Tools. So the magic here is my favorite way to use GDB is gdb.attach, which gives you a GDB session on an already running process. So there's also a couple more ways of interacting with a process with GDB that you can see here in the documentation. But the order of operations here is basically you start a process that you know that you want to connect GDB to. So the process starts, and then as I said before, it hangs on fgets. And you can only, it's important to note that you can only gdb.attach to a process that is hanging. So when it's waiting for input is the perfect time to gdb.attach. And you might be looking at this second argument here for the function. And what that is this is just a GDB script. This is the same thing as typing in commands into GDB. It'll just do this when it attaches for you. So that means no more retyping breakpoints every time you quit and reopen GDB. What I have here is set a breakpoint at main plus 65, hit enter, and then continue and hit enter. So this will just run the process, open up a GDB session, and then continue normally. So I can, but I'll be seeing everything that's going on. And then you can just step through the program normally, and send line will still send your payload, and you can see everything as it happens. It's super streamlined, super easy, makes stuff a lot better to use. So we're going to do a second demo here. I'm actually just going to show you guys what I ended up writing just for the sake of time. I don't want this to drag on too long, and there's a lot of overlap. But you can see here that we're, we have our shell code, and I'll show you guys a NOP sled. I talked about that in my last lecture, but didn't actually show you guys. So I'll be doing that in just a second. What's special about this one, oh yeah, I should mention that this binary is just the program that I went over on my demo in my last lecture. So this is the, I forget what that lecture was called. But what made that program special, and the hard part of that, was when you ran this this code. Yeah, this was doing a buffer overflow with shellcode. And you might remember that it gives you a marker, it gives you a stack address that you have to use to, well, you don't have to use it, but that really helps your exploit here if you use this and calculate your address of your shellcode from this. And since Pwn Tools is the greatest thing ever, you can just use receive line. That's right, we can take data from the output of a program at runtime and use it in our exploit. So what's going on here is we are taking, what this line basically does is it uses Python string slicing to take just the hex address here. And if you don't know about string slicing, here's a link to a blog post that'll, it's very quick and easy. You can just pick that up in a couple minutes if you're not familiar with Python. So this will let us save the address of marker. We can we have to convert it to base 16 before we run it through P64, and you'll remember that we had to add 20 to it to make it point to our shellcode. But then this makes setting everything up so easy. And then we can just craft our payload super easy here. So you have the junk, the address of your shell code, and then here I put the NOP sled, and then immediately after the NOP sled is the shell code. So that way, if the marker points to anywhere in the NOP sled, it'll eventually slide up and hit the shell code. And I'll run that with GDB on. I might have to change that. But another thing worth noting, I'll talk about after we do this. So let's exit out of that. Let's make sure that my exploit that I have ready for you guys has, okay, yeah, GDB attach is ready to go. So we'll do Python 3 exploit, and you can see it opens up GDB for us and then takes us to the wrong place. That's right, I forgot to fix that. Okay, sorry about that. For the sake of the demonstration, I had to get rid of the C/N here. Yeah, the continue here, so I can show you guys what's going on. Anyway, back to what we were doing. Python 3 exploit.py. So this runs our exploit normally, but opens up a GDB console, and will show us what's going on right when we attach it. But if we continue, we can see we break at main 105 like it told us to, or like we told it to, sorry. And then you can see we have a whole lot of NOPs here. So this pointed to our shellcode successfully, and if you look at the stack, you can see a bunch of 9 zeros, a bunch of NOPs, and then at the end of it, we see our actual shellcode. So we can just next instruction a bunch of times, but that's going to take forever. So let's do like next instruction 10, which will jump forward 10 instructions. Oh, and you can see that now we're in the middle of our shellcode, so that will run. And then on the final syscall, it will run bin dash, which is wonderful, exactly what we wanted. And that is, let's see if does it actually work? Yeah, wow, it gave us a shell. Awesome. The magic of Pwn tools never fails to amaze me. So that's, well, I think we're done here. So that's, hopefully that's as cool to you guys as it is to me. I hope I'm not, giving you a headache shilling Pwn tools so hard, but it's an awesome, really cool, just exploit development kit. I can't believe they make this stuff for free. Also worth noting is that this is all, I've been running everything with process. I already talked about this before actually, but there's also like, you can use different variants of process to run like a binary over an SSH connection or from a remote IP address. And that's what makes it so ideal for solving CTF problems, which is basically what your assignments in this class are based off of. So I think that's all I have for you today. Yeah. So no more talking about Pwn tools, but we will be talking about your homework, which you will need to write an exploit for in Pwn tools. And I will not be giving you the source code this time. Nihal taught you guys about Ghidra, and I didn't forget about that. So no source code, but Ghidra can be really hard to pick up, and it's pretty esoteric at times. So I'm going to show you guys just a little bit of, give you guys a little hint on the homework here. So here, hey everybody, Future Sam again. I was about to show you the homework, but it's changed since then, so I have to do it again. But I just want to show you guys the homework and how you should approach it, how to look at Ghidra, how to do some cool stuff with that, and just introduce you to this so you're on the right path when you sit down and give it a try. So first thing you should do is just run it to see what's going on, so that way you know what to look for when you're decompiling it. And it's going to ask us for a secret string. I don't know what it could be, and that makes me very sad. And it's going to yell at us too. Wow, this is a real mean program we've got here. So let's crack it open in Ghidra and see if we can figure something out. So first steps apply here. Just go into the functions list and go down until you find main, and then just double click on that, and that'll bring you to here. And just take a look and see what we can see. So we've got 3 variables here. If you haven't used Ghidra before, you'll see that undefined 8 will probably stick out to you. And all this means is that Ghidra couldn't figure out what kind of variable this is. So it knows there's data here. It doesn't know what. And we'll see if we can try to figure that out right now. So we can see that it's actually immediately initialized to whatever this is. So that's interesting. That could be any kind of data. And then it says, all right, what's the secret string? We know that. And then it does an fgets of 10 bytes into local 1A, which we know is a 10-byte character, right? Because Ghidra says so. And that sounds pretty right, because fgets gets, strings usually. So let's rename that. Well, local 1A is not a very good variable name, and it doesn't mean a whole lot to me. So let's just press L on our keyboards, and that'll let us rename a local variable. So I'm going to rename that to input, since it's letting us input ourselves whatever we want into there using fget. So that'll change that in here and even in the disassembly, which is very useful. So that's actually a big part of reverse engineering, is turning this weird obfuscated code into something more understandable. So then what happens here? It says ivar1 is equal to a string compare of local 10 and our input. So okay, there's a string compare. So that means that maybe local 10 is actually a string. And more than that, using our context clues, maybe local 10 is the secret string we've heard so much about. Now, to convert this to a string and figure this out and maybe we should to convert this to a string. There's a couple ways of doing. Obviously, this is hex, so you can't just copy and paste this as the secret string. So I have to find a way to convert this to letters, and then maybe, just maybe, if this was a string, like I think it is, you'd have to. It could be backwards and reverse because of little endian, and Ghidra doesn't know how to reverse that. So maybe you'd have to do that yourself. I have no idea, really. And then moving on here, it looks like if these two things are the same, if local 10 is equal to input, then it says correct. Here's a stack address in your overflow. And then it prints the address of local 10 and lets us put 200 characters into input. But we know input can only hold 10, so that's a buffer overflow. So then, yeah, it looks like that's what we're supposed to do here. We get the secret string correct, and it'll give us the opportunity to do a buffer overflow. And, this is another print off a stack address and a buffer overflow for free. And if we go over back to, if we open up vuln in GDB and then we hit it with checksec, let's see what's going on here. We have no NX, which means that we can run shellcode. We can inject shellcode and run it. So, maybe just like 2 homeworks ago, this is very similar to that. Maybe we could use shellcode and overflow it. I truly have no idea. This is up to you guys. I couldn't do a problem like this. You'd have to be really smart, which is why I'm assigning it to you guys. But yeah, enough about that. Hopefully this doesn't bring me back to slide 1. Okay, yeah, cool. So your goal here is to get a shell, as it always is. Make sure ASLR is off when you're doing this. This is not an ASLR challenge, though you actually can do it with it on. It wouldn't be that different, depending on how you do it, I suppose. You must script it with Pwn tools in Python 3. And this is actually a big one. I mentioned using shellcode. I tried this using Nihal's best shell code from whatever lecture that was, the first one or the second one. And you can't use shellcode that uses close on standard input. Standard input has to be open, or else Pwn tools' interactive function won't work. So I used the basic shell script that he has. I recommend you guys all use that too, because it gets the job done just fine for what we're doing. But yeah, that's all I had to say. I'm proud of you for making it this far. You guys are all Pwn tools pros. Now you can do like the real cool, like official hacking kind of stuff. And good luck on the homework, and have a good day.